We finished up our last, welcome to session 10 of lesson 2. We're going to talk a little bit more about optical properties. We finished up our last discussion talking about the dispersion curves and the variation index with wavelength. And again, we were looking at these two particular curves, and we noted that there were differences in the shape and form of the variation in index with wavelength. And sometimes what we need to do is not just understand what the index is at a particular wavelength, but we want to understand how the index of refraction changes over a wavelength region or a particular limited wavelength region. And the way we do that is a parameter that's referred to as the Abbe number. The Abbe number characterizes the dispersion in an optical material, and for the standard definition, the Abbe number at the D wavelength, again the 587 nanometers, is equal to the index at 587, or the D wavelength, minus 1, divided by the difference between the index at the F wavelength, the blue wavelength, and the C wavelength, or the red wavelength. Again, those are the D, F, and C are those spectroscopic terms that were in the table a couple of pages back. Typically, Abbe numbers range from 25 to 70. The higher the Abbe number, the smaller the change in index, so the less dispersive is the material, which is important because it introduces less chromatic aberration, this variation in focal length with wavelength. Conventional materials do have a positive Abbe number. In other words, the index is higher at the blue wavelength than it is at the red wavelength. Index of refraction decreases with wavelength, increasing wavelength with conventional materials. Now, there is a tendency for materials that have a higher index of refraction to have a lower Abbe number, so to be more dispersive. That's not a requirement, that just happens to be a tendency noticed among a wide range or most optical materials. Historically, when we talk about the Abbe number, it is defined in the visible wavelength region. So we have the N sub D and the F and the C in the previous equation. But the fact is, it's a very useful concept, so we often do apply it outside this region. My background is in infrared optics and in the 8 to 12 micrometer wavelength region. I would also typically calculate the equivalent Abbe number, which would be effectively a function of the index at 10 microns compared minus 1 divided by the difference between the indices of refraction at 8 micron and 12 micron. If the first term, the new term, doesn't have a subscript, then you can, such as the D I had on the previous page, you can assume you're talking about the visible wavelength region unless you can understand otherwise from the context. So for example, if you were reading a paper on infrared optics and they were talking about the Abbe number of germanium, you could readily assume they were talking about in the infrared wavelength region, especially since germanium doesn't transmit into the visible wavelength region. Another important parameter that is directly related to the Abbe number and the dispersion is what's referred to as the relative partial dispersion. And the relative partial dispersion is very, very useful in helping us understand how a particular optical material or set of optical materials will behave in an optical design. And what this does is it compares the change in index over some limited wavelength region to that over the full visible F to C wavelength region. So when we talk about X and Y here, I'm talking about a particular set of wavelengths whose range is typically less than that between 486 and 656. Now, where does this come into play? Well, most optical materials, when plotted in terms of index and Abbe number, fall very close to a line. And looking at the definition of a line as y equals mx plus b, we can define this relative partial dispersion as a function of the Abbe number and the slope of a line. Where this is important is if I want to correct, or we need to correct, the variation in focal length over more than 2 wavelengths, it requires us to use at least one material that does not fall on this glass line. So let's take a look at a plot of materials. But first, let's look at this calculation a little bit further, and then we will look at the plot of the materials. But this term we've added here is how far a particular material departs from that normal line. When you go to the manufacturer's data, you will find that they list these deviations over several wavelength regions, so possibly over the C to T wavelength region, the C to S, the F to E, the G to F, the I to G, and again, I'm not going to list them by wavelength number. They are on that table in your notes a couple of pages back. Now, when you talk about creating a line, you have to have a starting point and an ending point, if you will, and in the shot glass catalog in particular, the line is formed by connecting the K7 material and the F2 material. And here is from the shot catalog. What we see here in this direction is the index of refraction at the D wavelength. And here is the Abbe number. And we see over here we have our flint materials. Anything with an F is a flint material. And you'll notice this is sort of at 50 we sort of have a demarcation line. Everything over here is a flint material. Notice the Abbe number is decreasing as we go to the right. And most of the materials to the left of this demarcation are crown materials indicated with the K, with the exception of the materials right in here. Some of the colors associated with those, the dots, are listed here. The green materials are lead and arsenic free, which are the glasses signified by the N dash or the P dash symbol in the shot catalog. These are typically available materials. The red dots are the classical crown and flint materials. Some materials are less readily available. Some materials are more suited for molding than others. So this is sort of a description of this, and if you don't have access to a shot catalog, I would recommend you either go online and download a version or you ask them to send you one. Okay, so again on that glass map, the vertical scale was the index, Abbe number decreases to the left. You notice that there was a limited number of materials. There's a large part of the glass map that isn't occupied. Obviously, you can only use materials that physically exist. The flint materials are those whose Abbe number is less than 50, so to the right-hand side of the plot, or have an Abbe number of 55 and a relatively low index, so an index less than 1.6. Everything else is a crown. So here is an index of 1.6. So all of these materials with an Abbe number less than 55 and an index less than 1.6 are flints, as is everything whose Abbe number is less than 50. Now here is a plot showing that glass line, and it again goes between K2 and the F1 points. We have to have 2 points to draw our line, and you'll notice most materials are relatively close to that glass line, and it is the materials that depart significantly from the glass line or noticeably from the glass line that are very useful in helping us to correct for our chromatic aberrations across multiple wavelengths. And here is the same data again, but this time attempting to show you the availability plot as well. So again, all of this information I'm showing is from the shot glass catalog. Please feel free to contact any of the glass manufacturers if you'd like to get more information about the materials. because properly understanding the behavior of optical materials is absolutely key in doing quality optical design. Thank you very much. And this ends the lectures for Lesson 2, and I will meet with you again next week for Lesson 3. Thank you.